shall we start? So today we are very happy to have Professor Jae-Hun Jung from POSTECH, Math Department, and he will going to talk about today topological data analysis of time series data. So please welcome Professor Jung.
Okay, thank you very much. First of all, I would like to thank Professor Shin for the invitation and organizing this great seminar. And also, thank you for the respected professors and students and the audience. Thanks for coming. Today, I'm going to talk about topological data analysis of time series data today. And actually, I prepared 104 slides, but I don't know if I can do all these, but I try to skip all the details. You can take a look at the archival papers. Then I try to give you the brief idea on the line. Okay, so let's continue. Okay, so today I'm gonna talk about three things. Part one, PDA on music data, and music is also time series data, and then PDA on GW, the gravitational wave signals, and then last one is our recent work about exact multiparameter persistent homology. So we call this method EMPH. Okay, so actually, to introduce EMPH, I need to explain about the complexity about the persistent homology. So I'm gonna spend some time to explain the persistent homology. Probably some of you are already expert in persistent homology, but just in case, if you're not familiar with this persistent homology, I'm gonna briefly introduce what it is. Okay, I'm considering the time series data, and F is given by Ft, and T is an index set, and K is the index set, and then suppose that we have F, the time series data. This T could be time or any other indices, so on. And then usually this is what we are trying to do. Once this Ft is given in the physical space, right? So then we try to convert this node space to mode space. And then once you enter the mode space, and then you do some operations like a fast Fourier transform, and once you using the fast Fourier transform, once you get the mode information, then you do some operations for the mode space and then come back to the physical space, right? And for this problem, depending on the operation in this mode space, we can do some predictions and compression, anomaly detection, and other in the important business. Okay, so for example, anomaly detection using the filter. So low pass filter, then you can use the anomaly detection for using this filtering. This is just the first order. This is our filter. And then also, if you go to the FK in the mode space, then you can do some nonlinear projection, nonlinear filtering kind of. So this is Gibbs complementary Gegenbaum polynomials, and then you do some, some operations, and then come back to the physical space. So this is what we usually do for the time series data analysis, right? So from the node space, you go to mode space, and then do some operation, and you come back to the physical space. However, today, instead of doing this, I'm gonna do some embedding space. So once you have a time series data, then we go to the, instead of going to the mode space, we just go to the some kind of embedding space S, and then do some business here. So for example, for time series data analysis, probably the sliding window embedding is the most popular embedding technique with some geometric D. Okay, so this is my main the work for today. So given the time series data, we go to the embedding space and then do topological data analysis. Okay, so if you have any questions, then please interrupt me and ask the questions. Okay, so the topological data analysis, as you already know, has two approaches. One is a persistent homology using the homology, and then the other one is a mapper. Mapper is basically a graph approach, is a level set on a manifold. So today I'm going to focus on this persistent homology. Okay. So let me briefly explain the homology group. Just in case, I'm going to briefly explain this. Suppose that we have oriented K simplex, for example, zero simplex at the point, and then one simplex line, and the two simplex triangle, and the field triangle, and tetrahedron, and so on. So zero simplex, one simplex, two simplex, three simplex, and so on, n simplex. Suppose that we have this simplex. Okay, so then we can think of this module CN. CN is basically the suppose the R is a ring, and the X is a topological space, and the CN is the free R module generates all possible continuous images of n simplices. Okay, so and then you just collect all the simplices, and then we define the boundary map. Okay, so we use the boundary map. So the -1 is important because we consider the orientation. So this is the definition of the boundary. So on the vertices, you just remove one vertex one by one. Okay, so this boundary. So I'm going to give you some simple example. Suppose the two simplex composed of x0, x1, x2. Then sigma 2 simplex, this is a triangle, is x0, x1, x2. This is a simple exercise. Sigma 2 is x0, x1, x2. In the boundary map, then you just remove x0, and then like x1, x2. And then next one, you plug a minus sign, and then remove x1 and x0, x2, and so on. So this is the boundary. Okay, so once you have a boundary, the image, then you can apply the boundary map again. So then, as you see, again, x1 removed and x2, and the minus sign, x2 removed and x1, and so on. It turns out it becomes a zero. Okay? So in fact, this is the general statement. So for any n, this could be zero. So you apply the boundary map, and one more time boundary map, and then you finish this. Okay, so then you have a delta n plus 1 is going to be 0. So we can think of two things. One is the image, right? The boundary image. You have the topological space, and then you apply the boundary. So this is kind of image. And then delta n, something becomes 0. So you can consider the corner space, right? So image space and the corner space, two spaces. But this corner space is bigger than the image space. Then we can think of the quotient group. So that's quotient group is the nth homological group of X. So this is a quotient. So the bigger space and the smaller space, the kernel delta n and the quotient image delta plus. Okay, so this is the nth homological group. Okay, so let me just give you one example. So the reason why I'm going to give you this simple example is because I want to talk about the complexity. So S1 is close to the x0 and x1, x2. Suppose that we don't have the field, the triangle is open, x0 and x2. Then we have a three vertices, a 3 point x0 and x2. And C0 is composed of x0 and x1, x2. And this is C0. So by definition, C0, the boundary becomes 0. Okay, so this is no space. Okay, so then C1 is composed of these edges, x0, x1, x0, and x2. And then since this is open, we don't have a C2. Okay, so this is basically chain. And then, as you see, you can apply delta 0 to that C0, and then this becomes 0. And the C1, delta 1, this becomes the C0. Right? So we can compute this H0. So that's basically kernel delta 0 and the quotient between kernel delta 0 and the image delta 1. Okay, so this is the C0. This is the C0, right? This is the C0. And then they all becomes a 0 once you apply the boundary. So that means the kernel looks like a G3. Okay, so because x0, x1, x2 looks like a G3. The kernel space is basically the same as a C0. And the image, and then you take the image of C1, and then basically x1 minus x0 from the first element, and x2 minus x1, the second element, and so on. As you see, if you added these first x1, x0, x2, x1, if you added these two, then this becomes minus the last element. So that means that they are linearly dependent. Right? So this is, it looks like a G2. you have two linearly independent components. So this is the G2. So this is G3 and then this is G2. So this becomes G1. So this is the H0, zero dimensional homology. Okay, so how do we compute this one? So for example, delta zero, C0 becomes 0, right? So from x0, x1, x2, everybody goes to 0, 0, 0. Then this is going to be the operator. The matrix becomes zero matrix, 0, 0, 0, 0, 0, 0, 0. So the kernel becomes everybody going to 0. So kernel becomes 3. Rank of kernel becomes 3. And then what about delta 1, C1? And the same thing. So x0, x1, the one edge, second edge, and the last edge. Then you apply the boundary map. Then the first one becomes x0 as a minus sign in front because you have to remove x1 in the second time, and then that you get the minus x0. So this is minus 1, and so on. We can construct this matrix. So as you see, the first, oops, sorry about that. So you have two columns linearly independent. But if you add these two, if you add these two, then you get the third one. Okay? So then the rank of image delta 1 becomes 2. So number of generator becomes 3 minus 1 becomes 1. Okay. So this example is quite simple. However, if you have more than 3 points, for example, you have a 4 point, 5 point. Okay, so then what do? We expand this matrix. Okay, whenever you have a new simple system, you add this component in this matrix. So as your algorithm goes on, this matrix is getting bigger and bigger and bigger. So basically, the homology, the computing the homology is basically linear algebra. So in fact, to find this homology, computing the homology, the complexity is at least the cubic complex. Okay, so it's expensive. You have to do all the way the matrix operations. Okay, so this is quite expensive. Okay, I'm going to show you later. Because it's a complexity, applying this the percent homology to complex problems, the large size of the time series data is not plausible. So that's what we are proposing EMPH in the end of this talk. Okay. So for example, zero dimensional. So zero dimensional is a connected component. So if you have this kind of X, then you have in our case, you can just use Q. So then this is Q2. You have two connected components. So H0, zero dimensional homology becomes Q2 because you have two connected components. And then, however, you have one dimension, you have 3 holes, right? 1, 2, 3. Then this is going to be Q3. So if you fill one of them, then you still have the two components. So H0 becomes Q2, but H1 is you have only two the empty cycles. Then this is going to be Q2 and so. Okay, so so this is going to n-dimensional homology is basically the extension of this 1 and 0 dimensional homology and so on. Okay, so however, the problem is that this is the data on the left hand side. This is a point cloud. This is the data. Okay, so once this data is given, we do not know which one is representing homology of this data. Okay? So that is why we introduce this filtration. So we introduce the filtration. So by increasing the filtration, we try to construct a simplex out of this. For example, this is explaining the Rips complex. Then using some radius epsilon, by expanding this epsilon, if there is overlap, then you just connect to this point and then construct the simplex. Okay, so once you have a triangle, then you just fill in, and then once you have a tetrahedron, then you just fill inside and so on. So as you construct this simplex, at each time you compute the homology. That is known as the persistent homology. Okay, the reason is because we do not know the representative homology of this data. So the persistent homology is quite a useful concept. Okay, so in this talk, I'm going to use the Viters-Rips complex. So just this is the definition. You just use some distance matrix in the matrix space. You use some matrix dx, the less than epsilon, then you just connect that. So I'm gonna explain. Okay, and also percent diagonal and percent barcode is a one parameter collection of percent group. So each filtration will corresponding to the homology. So if you collect all of them, is called the percent of k-dimensional percent homology. And then this percent diagram, the DGM, I'm going to use this notation DGM or barcode. It's a multiset. So I'm going to explain. Okay, so just to take a look at these four squares. Okay, so each one, so just use a two norm, and then this distance is basically 1 and 1 and 1. The diagonal is a square root of 2. Then you just use the filtration. So for example, epsilon. Epsilon is the free parameter. So if epsilon equals to 0, the beta, we out of this we try to find the beta 0, number of connected component, and beta 1 is the number of one-dimensional holes and so on. So for example, at tau equals to 0, then all the distance should be less than tau, but in this case it's not possible. Then you cannot connect at any point. So when tau equals to 0, beta 0 connected component is 4, and then there is no hole, so beta 1 becomes 0. And the tau equals 0.5, still the minimum length is 1, so that I cannot connect to anybody. So beta 0 equals 4 connected component, and the beta 1 equals still 0. However, tau equals 1, then everybody is connected, and then this becomes 1 component. Then this beta 0 becomes 1, and beta 1 equals to 1, because you have one hole. And then if tau equals square root of 2, then connect this way or the other way. Okay, so then you have still one connected component, and the beta 1 becomes 0 because you just fill inside the triangle, right? There is no hole. The hole disappeared. So hole appears at tau equals 1, and the hole disappear at tau equals square root of 2. So we call this starting point is a birth, and then the death, the tau, the vanishing point is death, the birth and death. So this is the birth time, and then death time. Okay, so this is a barcode. For the one-dimensional case, so you have a whole this is a one-dimensional hole. Then the hole appears at tau equals to 1, and then dies at square root of 2. So this is a one-dimensional barcode, and then this is known as the length is basically persistence. Okay, so in this case, we use a discrete value of tau, but if you use the continuous value, then you can get the zero-dimensional. Up to tau equals 1, you have a 4 connected component, and then afterward it becomes 1 component, right? So even though tau becomes infinity, you still have the 1 connected component. So the last one, burst time becomes 0, and then death time is going to be infinity. So this is known as a barcode. And then if you plot this burst and death, okay, in the domain, okay, x-axis is the burst time, and the y-axis is death time, and this is going to be percent diagram. So the percent diagram and the percent barcode basically they're the same. So this is a multiset, meaning that you basically have a 3. You have a 1, 2, 3, right? 1, 2, 3, 4. They're all degenerated. So they're all degenerated. The last one. And then you have a 1 cycle. Okay, so sorry about that. This is not correct. So this is a percent diagram. Okay. So actually we need a stability theorem. So okay, so let me just briefly, and we usually use the bottleneck distance. Okay, and then we have the stability. So if x and y they are isomorphic, then we have d1 and d2 they are close to each other in terms of a bottleneck distance. So even though you have a small perturbation, just a perturb some little your data, then still the diagram, the percent diagram, changes just slightly. Okay, so we can rely on this method. So that's the stability. I'm gonna briefly mention again in the music data analysis for the stability. Okay, so this is just the introduction. So, I didn't see the work, so I'm gonna check my. Okay. Yeah. So any questions so far? Okay. There is no. Okay, so now I'm gonna take a look at this music data. So we apply this music data. The reason why we apply this TDA to music data is because music is characterized by the repetition of a melody. So once you have a repetitions, then in terms of mathematics, it looks like a cycle, like a loop, and so on. So this TDA works very well for the music data. Okay. In fact, actually, TDA is not the magic. So if you have some, for some data, TDA works very well, but for some data, TDA doesn't work at all. Okay. So music is good for using this TDA. Okay. Okay. So the music data. Okay. So I'm gonna introduce some problem given to us about 3 years ago. Okay, so in Korean music, we have three different pieces of music. The first one is 수연장 지곡. And so this is the music piece that was played in front of a king. Okay, so this is a 수연장, and the second one is a 송구여 지곡. And the 송구여 지곡 is basically same as a 수연장 지곡, but one octave higher. So basically they are the same. Of course, so there are some variations, however, they are basically the same. So this is known as a dodori music. Dodori means that repetition, come back, progress, and come back, but with some variations. So this is a dodori music, and then this is a taryon. So if you go to the YouTube and then try to listen to this 수연장 지곡, 송구여 지곡, and taryon, then this taryon looks like dodori music. However, this taryon is not belong to dodori music. Dodori is a really, very mysterious, strange, very peculiar, very unique type of music. Okay, I recommend you to listen to this music. So if you listen to this music, you hear that something is being repeated during the music process. And also, even though the music ends, your brain is still listening some repeating melodies. So the question is that what's the main characteristics of this dodori music? There is some Korean music theory, but almost a rare Korean music theory to explain this dodori type of music. So we try to use this TDA and explain why this is so unique compared to other class of music. Okay. So in that case, again, as I said in the introduction, embedding space, finding the embedding space is really important. For the music, what is the embedding space in this case? What do we do? So how do we find the S? Okay, so 수연장 uses only 5 units. It's really simple, G sharp, A sharp, D sharp, and F. They just use 5 units and then different octave and the different durations. Okay, so they use this one. Okay, how do we construct this embedding space? So this is what we did. So for example, I'm gonna draw this one. So for example, music is a G sharp 3. The first one is a G sharp 3. And the second one is, for example, A sharp 2, and then F, and then D sharp, and so on. Suppose that this is the flow of this music.
What is the number? What does this number mean?
G means
3, 2.
octave.
Okay.
This is the normal octave, and this is the octave lower. Yeah, this is okay. So then, so this is what we did. So G sharp 3, and then some kind of duration. So as you see, this one, and this music notation was invented by King Sejong. So his most important famous invention was Hangul, Korean writing system. And then besides this Hangul, his second greatest, maybe call it second greatest invention is the Cheonggam. Okay, so this is quite opposite. The Western music, if you look at the Western music, and for example, then you see that this pitch is visualized. You can see that this is the the E. And then you can see that this second one is higher than the first one in terms of pitch, right? However, you have to learn the music theory to know that this is shorter than this guy, the second. Because the first one is shorter than the, right? So pitch is visualized, but duration is inscripted, the Western music notation. However, this Korean music is quite different. So if this is one, the beat, then you just type, for example, Korean music, some, for example, this means that, okay, so for the duration, you just use the space of this squares. Okay, so in this case, this is half, right? We just use only half. So for example, this is now. Okay, so it's quite opposite. The Korean, the system is quite opposite to the Western system. Okay, so in this case, the pitch is inscripted, but duration is visualized. The reason is because in Korean all the time, and it's the same as in China, the space and time, they are the same concept. But the Western time, the time and space, they are separate, but we are the same. So to reflect this one, he invented this way. So in this case, so we look at this music and then find the pitch, for example, the sharp 3, and then this is take as a 1 beat. So this is 1. And the second one is a sharp 2, but this is 1/2. This is 1/2. So as time goes on, you have a different the element. So we call this as node. And then this is a node. So maybe you can repeat the same node. Okay, and then once you have this node, for example, Jae-Hun Jung has 33 different nodes. So you have a 30 different nodes. The first one is N0, and the second one is N2 and N0, and N1, N2, and all the way N33. Okay, so, and then what about the distance? We try to find the distance N0 and 1. Okay, so there is some, you need some imagination. How do we define the distance? So this is what we define. This is how we define the distance between these two. So if you look at this one, F and D sharp, and then F and D sharp, then actually they come together side by side once, and then twice. Okay. So look at the frequency. F and D sharp, for example, this is F, and then this is the D sharp. Oh, they come together twice. Then you connect these two, you are connected. And then this is twice. Okay? And so on. And the distance, if you are come together frequently, then we interpreted this as the distance is shorter. So we just take the reciprocal in this way.
So all these NIs are all distinct?
Yeah, or they are distinct nodes. For example, this is same thing, G sharp 3 and the G sharp 3, but this is the duration is 2, duration is 1, then they are different. However, if they are 2, then they are the same node. Okay, so then I defined all the node and I will define the distance. Okay, you define the metric. Okay, so is this a good metric? I don't know. We are still working on this problem, but anyway, we define the node and then edge and then distance. Okay. So
What about the stability?
yes, that's a good, that's a good question actually. So we are working on this problem. So okay, so if you have a small part, for example, in the Korean music is quite different from the Western music. You know, you can recognize this term, 시금새, 장시금. It's kind of the ornament. Okay, so there is some special notations. So then, if we have a special notations, then we expand this guy. Oh, this guy has this ornament and so on. So what about if we still perturb this guy? So then we have, this is a preliminary work. We have the stability. We have the stability, and we prove the stability. We have a little perturbation, But we have a stability. But this stability, so we're gonna put this in the archive soon, but little difficult because everything is discrete. So, okay, so I'm gonna let you know once we have this paper on archive, and then you can take a look at the proof. We have the kind of proof. Okay. So anyway, so that is a good question actually. We have to worry about this stability anyway. Okay, so then. Okay. So this is the how we define the node, the pitch and length, and then this is extendable. If you have an ornament or Shigim sensor, you can expand in this guy, and then you have to prove that once you perturb this guy, then do we have a stability? The answer is yes, we have a stability. And then this is D, they defined this way: the distance between, for example, distance between the N3 and 2 and 1 and 0. They are not directly connected, for example, then you have to find the minimum path between these two and then add the distance between. So this is how you define the distance. Okay, so then you have a point cloud, right? And then with the metric distance, then this is a 0-dimensional barcode, and then this is a 1-dimensional barcode. If you look at this 1-dimensional barcode, we have 8 the element 1, 2, 3, 4, 5, 6, 7, 8. And I showed this to the TDA expert, and then they said, oh, this is the really small. The percentage is really small. That must be noise. In fact, this is not noise. Actually, this is a really important cycle melody. And so the mathematicians think this is noise, but musicians think this is a really important melody. So this is not noise. So we have A, we found A cycles. Okay, so this is the cycles. A cycles. They are connected to each other. So A cycles. Okay, so now to solve this mystery, okay, so we introduce overlay matrix. So some mathematical proof of this overlay matrix in this archive. Okay, so this is Jae-Hun Jung, and then this is what we did. This is the music flow from time series from 0 to the end. Music
Sorry,
start.
I missed the.
Yeah, sorry about that.
So, how do you make this persistent diagram, a persistent homology? That you use Rives, Victoria's
Rives complex, yeah, Rives complex.
with all these measures and.
Yeah. This time using this material. Yeah. Rives complex. Thank you. And then this column, this row is cycle 1, 2, 8, right? Okay, and then this is a music start and music end. And then you saw the cycles, right? All these cycles, and then you look at this all element. So, and then if you look at this consecutive the node, and then if this cycle 1, so somehow in this music element, if cycle 1 is repeated, then you just color. So this is what we get. This is known as overlay matrix. And then this means that this is the interpretation. Okay, as time goes on, as music progresses, the cycle appears, but in an overlapping way. So this means that this one is a monophonic, 한선율. However, when the people listen to this music, it looks like instead of the monophonic music, it looks like it has a harmony. Okay, so Korean music is known, very well known that Korean music doesn't have harmony, but it looks like harmony. However,
Y coordinate is time.
Y coordinate is a cycle. So this is a cycle. This A cycles, right? This is a cycle number 1, number 2, number 3. Cycle number 1, number 2. So this means that. Okay. So first of all, cycle 1 appears when the music starts, and at the same time, cycle 7 is cycle 7 is also playing. They are overlapping.
That indicates the cycle.
This is A cycle, and this is time. So this means that when you listen to this music, you think maybe, oh, he's playing the second cycle. However, he's playing the 4, 5, 6 as well. Okay, so this is the 도드리 music, 수연정지곡, 송묘지곡. But 타령 was not the 도드리 music. It's really surprising that there is nothing is overlap. As you see, nothing is overlap. Okay, so these two are totally music, then we have overlapping. But the last one, it doesn't have any overlap. So that was really an interesting finding, actually. Okay, so this is one way to explain, to solve this mystery, why totally is so unique. Okay, and then, so this is really interesting. This is completely zero, but you have overlap matrix. Okay, and then we apply this Unisang Karak, and then you can apply this technique to the Western music. Okay. So I spend too much time on music. Any questions? So I don't explain this today, but once you find this over a metric, this is basically composing a principle kind of. So then you can train the machine with this composing principle, and then you can generate this AI music. So we generated AI music, and then we added 2 music concert, one in Pohang and one in so. Okay, so then now this is part 2. Well, I'm gonna skip the part 2. So this is the gravitational wave detection problem. Okay, so I'm gonna skip, but I have to explain. Okay, now for this gravitational detection problem, we use a different embedding. The time sliding window embedding. Consider this a sliding window embedding. So this is the definition of a sliding window embedding. So ft is given, and using 2 parameters m and tau, then this ft is mapped to the vector r m+1. So this is sliding window embedding, right? Okay, so you have all the time series data. Suppose time series data, and then using the slide window embedding, this is time series data, and then you can construct this huge matrix, right? This is what my point cloud. This is my point cloud. Okay, so this is one way to construct the point cloud using the slide window embedding. So for example, how about this cosine LT? Then using this m and tau, you can decompose this cosine using the cosine formula, the cosine and sine. So these 2 vectors, basically, you can decompose this is a cosine and the sine using u and v. U and v not necessarily linearly independent yet. Okay, so for some value of m and tau, they could be linearly independent. So this is the one. And then suppose that you have a sine and cosine, and this is a physical space, and then this is the embedding space. As you see the some the cycle structures. Okay, so once you have the time series data in physical space, and then using the slide window embedding, and then reproject this data into the embedding space. Then we apply the percent homology. Okay, and then we get the let me just skip all this technique, but you have to prove the stability and so on. And then we had a really nice result for the gravitational wave detection problem, much better than the CNN. This is a CNN result, and this is our TDMA. So this is really better. However, this is the problem actually. We explained why this works recently, but the computing percent homology over the Beatrice Rips complex is computationally really expensive. When the embedding dimension m+1 and the size of the given time series data f is really large, then it's not possible. So those, in many cases, percent homology with the Rips complex is not plausible. So what do we do? So this is why we did listen.
Excuse me. You have this big matrix, right?
Yeah, this is big matrix. Yeah.
All the column vectors are the elements. I mean, point cloud. Right?
Yeah, that's the point cloud. So
point cloud consists of the number of columns.
That's right. So this is for example, yeah. So this is the m+1 vector. in the n+1 space,
Right.
then you have
One point.
n minus n point.
Right, yeah.
Okay, so that's my point cloud, and then we apply the percent homology. And it's really expensive. And what do we do? Okay, so this is what we did. Let me briefly explain. So as you see, to compute this one, you have to do linear algebra. So the complexity is minimum complexity is a cubic complex. We cannot depict this guy. So this is what we did. Maybe Fourier transform is fast. So why don't we just use a Fourier transform? So this is the idea. Okay, so let me explain this one. So we try to use FFT. So FFT is faster. So is it possible to FFT to compute this homology? So this is what we did. So first of all, we copied this theorem from Pereira and Hara. So even though you are using truncated Fourier, then it's okay. So as long as you have a large n, and then this is bounded, right? So instead of a real f, you can use the Fourier. So this is fine. So when you have a large n, okay, so instead of a real f, we use the fast transform f and then construct the continuous image of f. Okay, and then look at this. We just look at the cosine function, right? Cosine is decomposed in the sine and cosine, right? So UL, the UL and the PL, okay, they are linearly independent if and only if m is greater than 2n. Okay, so that's the first one. And also, if you expand this cosine L in the slide window embedding, then you can composition the cosine and sine UL, PL, right? So then this slide window space is spanned by ULVL. Okay, so this is we call this each space PL is L plane. That's the one. Okay, then consider this sliding window embedding again. Then you just choose a very particular one. Tau equals to 2 pi divided by m+1. Then, in general, the cosine and sine in the embedding space usually becomes ellipse. We cannot predict the shape, right? However, if you use a very particular parameter, then they becomes all the way circle. This is good. So we try to use a very particular parameter, and then everything is a circle. Then using that choice, okay, they are orthogonal. Okay, and then they all become the circle. And also we define the L plane becomes orthogonal. Okay? So, and then one more thing. So once you have this point cloud in the embedding space, we have using the centering map. Everybody's aligned to the center. And then after this is slide window embedding and the centering map, then you end with this one. And then XL, YL, they're orthonormal. So this is very good. And then this R is basically Fourier coefficient. Okay, so that means that this guy is after the centering, and then this guy is our embedding space. Okay, so this is my point cloud. Okay, so they are actually they're all orthogonal, and the image is a circle, and they are defined on the n torus. Okay, with the metric D2, what it makes, they are basically topologically the same. Okay. So we are trying to find this the F, right, embedding space, but that can be given by the product of each. That's the key point, and each one is basically circle. So if you have the circle, I'm going to finish it soon. If you have the circle, for example, S0, then S0 is given, then you just have, for example, 1, 2, 3, 4, 5, 6. Suppose you have n polygon, then the burst time is basically this one. Okay, so this is L. L is the burst time. So once you have the L, then you have one cycle. Okay, so when this cycle dies, is basically the bottom line is basically triangle. the unit circle is basically 1, and then this is square root of 3. Okay. So the dash time is a square root of 3, and then the burst time is basically this length. However, if we have the infinitely many infinitely many points, basically, then burst time is basically 0 to square root of 3. Okay. Instead of computing the homology on the circle, we do the exact. So that's the idea. Okay, so this is the barcode. We would like to have the barcode of this slide window embedding space, but that's a product. So you have all the the barcode of the product space. For example, one dimensional, then this becomes 1 0 0 0 0 or 0 1 0 0 0. Suppose you have n torus. If you need a one cycle, then the first one is one cycle, and the other one is 0 0 0. Or if you add all the then. Okay, so actually the I don't have time today, but all the complexity comes from this actually. This is expensive. Except that everything is basically cheap. So we can compare to this one exactly on the circle. Yeah, so simple algebra, you can do more. Okay, so then, and then this one. Okay, so we can, okay. So we have, this is the square root of 3 comes from square root of 3. Okay, so this is the already 50. So I'm gonna give you some conclusions. Okay, so for example, this function cosine t, 1/2 cosine 2t. Okay, usually the slide window embedding, what do? We do apply the slide window embedding. Okay, and then apply the risk complex and compute the percent homology. We don't do that. This is what we do. Okay, cosine t, this function, this plane, cosine t is basically, we know this one 0 to square root of 3. And then what about 1/2? 1/2 is a shrink, right? The circle is a shrink. The radius is shrink. The radius is shrink. So then added these two. That's my barcode. Done. So you don't need to compute any homology. So in this case, you can do under any ray. Actually, in this case, you can do. This is the straight line, but you can also do this curved one very easily. Okay, there is no computation at all. So I'm going to show you this is a really big data, fMRI. So applying the percent homology to fMRI is not possible. So they don't use this the risk complex for fMRI, but we did. We did. And this is the EMPH, the computational time, and then this is the usual percent homology. But the accuracy is basically similar or even better. Okay. So time series data, what's the embedding space? It is quite useful for time series data. And then EMPH, using EMPH, we don't need to compute the actual homology. Very expensive. And then what is the point of optimal curve? Is still remaining problem. Okay, sorry about that. I passed a little time, so I'm going to stop here today. And then thank you for your listening.
All right, let's thanks to the speaker. Are there any questions from the audience?
It's multidimensional system, with well-known theoretical difficulty.
Yeah,
and
sure.
So does it escape, your method escape that difficulty, or?
Yeah, so this is basically multi-parameter percent homology. It's basically method carrier. This is what they need. So if they have a different parameters, these many different parameters, and then they use many rays. And then they compute this homology along this ray.
Along this
one dimension. Because we don't have any
discrete.
no. So just one, all of one. Yeah.
So yours is also same using one.
We are the same. However, the difference is that we don't need to take any time to compute the percentage. We just use the exact one. Yeah. And also, since they do not know which one is optimal, they have to use many different the percent homology.
Yeah.
However, we are very flexible to compute this curve. So that means that maybe if
along that curve.
yeah, along the curve. And then our conjecture is that the data, there exists some optimal curve on the filtration space that represents the data where we do not know whether this is good, this is good. We do not know. And then we do not know whether this straight line is bad. But if this is a curve, the previous method is quite hard to compute the percent homology. But in our case, it's quite flexible and computationally very cheap.
Very good. Very good. Yeah. So your paper is on the archive or
The archive.
but I
Yes, sorry. It's archive.
maybe I can search for your name.
Yeah. So we have
yeah.
sorry. So we have a
Going back to 100 pages.
yeah, this one, yeah. This one.
General, like,
Yeah.
what is the
Exact multi-parameter percent homology.
parameters?
Fundamental
Okay.
Yeah.
What about the time data such as a length? I mean,
Yeah, that's a good question, but we do not know it.
yeah, because it does not have repetition.
Maybe I don't know. So one thing is that the usual the percent homology on the slide window embedding space is equivalent to diagonal ring to our method. So the people are computing very, very particular one. So our case is really general. So one of them, but this equivalence, we show that this equivalence on the Rips complex, but if you change the data, different complex, we do not know what's going to happen.
Are there any questions?
There's one question from an online audience.
Yeah.
Yes.
Code. Okay, can you go ahead?
Yeah. So the beginning of the talk, you mentioned how you took music, Korean music, and apply an algorithm. What about Western music? Do you have a pre-process? Do you have code to pre-process Western music so that it can be used in your algorithm?
Yeah. So thank you very much for the good question. So yeah, so you can apply the same technique to the Western music. So this is the one. Yeah. So this is a piano and flute. Two piano and two flute. So you can apply the same thing, and then you can get the overlay matrix. The
Okay.
pass is straightforward. It's quite straightforward. Thank you.
Thank you.
Are there any other questions? Let me
Okay.
quickly ask one question. It's very interesting talk, and thanks so much. So I wonder if I understand correctly, after you process the barcode analysis and see the patterns out of it, then those components, and based on those components, can we utilizing those sources to create the new music?
Oh yeah. That's what exactly we are currently doing.
That's what you did.
Yeah, we did that, yeah, we did the AI.
And
music.
then how we match the ordering depending on our like which pattern goes first or because for example you have 8 patterns.
I see.
Which one
So
goes simultaneously not.
so we are basically that's basically we are using some deep neural network. Yeah, not only just this. So you need some machine learning technique combined together.
Interesting.
Machine learning and also TDA. The TDA and machine learning.
TDA has one layer or
TDA is this is the one. See, this is the kind of one that the features that the machine is trying to learn. But this characterizes the dodri music, and then this characterizes the kind of non-dodri Italian music. And then using this one, we match the data. And then there's a lot of things that I didn't mention today. So 장단, beat. We have to consider the 장단 and the beat. And that's also important. Everything put in the deep learning algorithm, and also you apply this. Yeah.
Thank you very much.
Okay,
It was
yeah.
very fascinating.
Okay, all right, thank you. Yeah.
All right,
Thanks a
let's
lot.
thank the speaker again for a wonderful talk.
Okay, thank you.